All right, in this video, we are going to look at the circuit above. And what we want to do is we want to, first of all, theoretically calculate the time constant. And then we want to experimentally do it. So we'll use a modeling program on the iPad. It is free. It's called Multisim Touch or Multi-Touch. But we're going to just go through it here. And basically, so yeah, go ahead and download it and play with it a little bit. But basically, we have a scenario where we have ourselves a resistor, and then we have ourselves an inductor. Okay, and it's on a square wave. Or it has a function generator. And so this is our resistance, and this is our inductor. The time constant for this is L, or the inductance, over the resistance. Now the resistance is 33,000 ohms, and the inductor is 100 times 10 to the negative third henries, or 100 millihenries. So we're going to put those numbers into tau, and when we do, we end up with 3 microseconds as far as a time constant. Now, this is how we're going to verify this, experimentally verify it. It takes approximately 5 time constants, and those are 5 taus, for this phenomena to take place, for the inductor to completely get rid of all of its energy. So this is about 5 time constants. So what we'll do is we will measure what's happening between here, and whatever that number is, we'll divide it by 5 in order to find the time constant. So let's just say that this is some number here, and we're going to divide that number by 5 to see how well it corresponds to our time constant. Now, the idea is that you would be doing this on a oscilloscope. So you can hook this up. You can put a probe right here, okay, and you'll have your ground right here, but you can put a probe on this side, and you would be able to tell what was happening in that experiment, or on the oscilloscope. You'd be able to see it. So let's just go ahead and let's do this. It didn't really work well for iCircuit, so we're not going to use iCircuit. And nope, that's the wrong one. That's Virtual Bench. It's not in that one, it's right here. There it is. It's Multi-Touch, and it's free. It's by National Instruments. Okay, I'm going to start up a new circuit here, and I think that we can call this circuit edit. So we're going to call this circuit our LR circuit. Double tap on there. So I'll just, no, I don't want to delete. I should have said done. So let's start this up again. And let's call this, we will call it, no, I better call it something now. Shoes, edit. I've built the entire circuit and then deleted it by accident. So this is going to be our LR circuit. Say done, tap on that, and now let's go ahead and build this circuit. All of the components are not going to be the same. So when we think about our voltage source, this is going to end up being a pulse generator. And we'll change this pulse generator to an initial value of a negative 0.5 volts. And then we'll do we have the initial value, the pulse value, and the pulse width. And so right now, we'll just leave everything else the same. It's kind of, I don't know how to put the frequency in this particular one, but that's okay. Okay, so we could put it in the pulse width, but aside from that, let's just keep going. And let's put in the next thing, which is a switch. So I'm just going to choose this single switch here. And then the next thing is a resistor. And we know that this resistor is just going to be 33 kilo ohms. Okay. And then the next thing will be an inductor. Okay, we're going to double click on that, and our inductor has an inductance of 100 millihenries. 100 millihenries. Okay. And let me see if I can squeeze down a little bit. And the next thing we need will be a ground. So our ground will be here. So I'm basically just looking at the circuit up there. So let's go ahead and let's connect this circuit together. All right. We already know what we're expecting to see. Let's see if we can at least simulate it. All right, so now we have our circuit here. We need to put a probe on here. We want a voltage probe. So we're going to put our voltage probe right here. Okay, it's not going to quite simulate the same as the other circuit, but that's okay. Let's just go ahead and go to our, let me go back. So it started the simulation, okay? And now you see that we have these curves here, all right? So that was similar to what we had right here. We have a curve right here, an exponential curve. Now the exponential curve near zero is difficult to work with, so I'm going to choose the one in the center here. So I'm just going to squeeze and pinch and all those good things. So let me go ahead and move these cursors over. This is how you can measure also with the oscilloscope. So I'm basically just widening it. So this is the same thing. If I wanted to, I could just, let me see, can I move down? Well, no, this is all we have. So let me go ahead and continue with this, okay? Make this a little bit bigger. Might as well make it big enough to see everything on the screen so we can get us a good measurement. So that's all. We want to see when this particular item hits zero. So let's see what our measurements are for this. Zero appears to be somewhere back here. Okay, so it's in between here. It's coming down, and it's going to rise to zero. And when I say rise to zero, this is like its maximum. Then it's going to rise, and it's at a negative potential right now. It's going to rise to this location right here. But zero is somewhere in between here. I'm just going to choose zero to be right here. It's pretty flat all the way across, but it looks like it's just at zero right here. So we'll stop right there. Okay. And now we can look at our delta x, and our x is the time, okay, and we have voltage on the y. So our delta x for our cursors is 14.02 microseconds. So if I just go back to a calculator, where is my calculator? Let's go back to a calculator here. Okay, and we had 14.02 divided by 5. Okay, that's about 2.8 microseconds. So if you look at that, the time constant is verified out to 2.8 microseconds. So if you're going to look at the measured value, it would be 0.00000028. Okay, and that's what it'll be for 100 milliohms. We'll do it for 50 milliohms in just a second, and then 33 subsequently. But you can go ahead and try to calculate it, try to guess what it's going to be, and then we can measure it to see if that is going to be the case.